So now we're going to look at thunderstorms. So we can have single cell thunderstorms. So now we're going to look at thunderstorms. So we can have single cell thunderstorms, multi-cell and supercells. A single cell is a single CU which turns into a CB and then into a thunderstorm. Has a nice short lifespan. It's split into effectively 3 stages. The development stage, which is predominantly the updrafts, and then they last about up to 30 minutes mid-latitude. You have the mature stage, so that's where we're getting that up and down drafts. We're getting the rain or virgo rain, which doesn't actually reach the surface, cold gusts, and that lasts up to about 30 minutes as well. And then we have the dissipating stage, which is predominantly downdrafts, and that lasts for about 2 to 3 hours. One of the questions that can come up as well, but it's the thunderstorm will move in the direction of the 10,000 foot winds. A multi-cell, so it's a group of multiple cells or squall lines. You usually see them at a front, and each cell is at a different stage in its cycle. The different cells will dissipate as a new cells form, and it continues the life cycle of the multi-cell storm, which makes it last longer. But each individual cell will only last as per a single cell would. And then supercell, basically it's got a deep, persistent rotating updraft known as a mesocyclone. You've got that warm air below, cold, dry air aloft with strong upper winds, and it can last several hours. Not something we really see in the UK. So just avoidance, so again some figures you'll need to know for the exams. Avoid them at 10 nautical miles low level, 20 nautical miles high level or above 20,000 foot, and by 5,000 foot above the thunderstorm itself. Thunderstorms at the ITCZ, the Intertropical Convergence Zone, only last for about 15 minutes individually. Hazards. So remembering whilst weather, we're going to get rain, cloud and pressure changes. Hail, which is going to give us impact damage. Icing, so it can increase all mass of the aircraft and obviously change the aerodynamics, making it worse. Lightning, so predominantly between plus 10 and minus 10 degrees, and it's going to get potential damage to the avionics. Squalls, so we're going to get that severe downdrafts and we're going to get wind shear. Turbulence up to about 20 nautical miles around. And electrical, we're going to get static electricity and St. Elmo's fire, that blue glow around windscreens. The requirements. So we need a deep layer of instability up above 10,000 foot, or preferably all the way up to the tropopause. We need high moisture content, and we also need a trigger action, something to make it happen. And the 4 trigger actions we look at are convection, orographic uplift, frontal, and convergence. So looking at convection first, here we've got our sun heating the surface. Warm air starts to rise, creating our CB cloud. It can happen over the sea, where when the temperature is high, and that's as basic as it is. We get orographic uplift, so again think about that fun effect as it gets forced up. So we need about 15 plus knots. The air gets forced up, cools, and we get that cloud forming, that unstable cloud forming over the high ground. Problem, likely in large number on mountainous ranges, so avoiding can be difficult. Frontal thunderstorms, so again we've got our warm tropical maritime and a polar maritime coming in. It's more dense, this polar maritime air, so it's forcing that air up. The problem with this, you can see if we've got different layers of cloud on that front, is our CU into our CB can be embedded. And last one that we've got is convergence. So you can see we've got a trough here, so an area of low pressure and poor weather, all converging together, forcing it up. And we're going to get thunderstorms on that trough line. So again, if you're looking at another way of looking at it, we talked about sea breezes earlier. So we've got, again, the Cornwall coast here. We've got different pressure areas from high through to low. So we're getting 2 sea breezes on this northern part of the coast, on this southern part of the coast. And that's going to give us those unstable thunderstorms forming inland. So we talked about squalls and microbursts, and that's actually probably one of the bigger risks, especially if you're in a helicopter. So squall or a microburst is an extreme form of wind shear generated by that slug of descending air from the thunderstorm cell. Diameter about 4K, lasts about 1 to 5 minutes. Feet per minute, 3 to 4,000, up to about 60 knots. In fact, the air is colder than the surrounding air, which is why it's that slug of descending cold air. You can also get a microburst, which is higher wind, longer duration, and larger area. So the way to think about for us here is whether you're in a helicopter or a fixed-wing aircraft, and we want to land at our airfield here, and we've got a thunderstorm. That would ideally the flight path we want to take. So we start our approach, we set our throttle, our power, and we start descending. However, at this point you can see we've got a headwind with that squall. So if we've got a headwind, we know our indicated airspeed is increasing. And if we don't do anything to the power, we will start coming above that glide path, we'll be climbing over it. So our headwind, our indicated airspeed increases, our aircraft will climb. So our pilot is now going to reduce the thrust more than he normally would on that glide path to stay on that glide path. At this point here, you can see as we get through that initial part of the squall, we've lost that headwind. We're now into more of a downdraft. But if we're losing our headwind, we can see our indicated airspeed is going to decrease. If we don't do anything with our IS decreasing, our aircraft will descend. So the pilot now needs to increase the thrust to stay on the glide path. However, it's already lower than it normally would be. And at this point, as he starts to move on, we're starting to get a rapidly increasing tailwind. So that means our IS are going to decrease even further, quicker, and our aircraft is going to continue to descend further, and we may not have the actual power to get out of it. So that's why if you get into that area, it's basically just go to max power, leave everything where it's set, put the nose onto the stick shaker, and hopefully climb through it. Not exactly possible in a helicopter as much. And that is our thunderstorms.